Hello everyone, how are we doing today? So if I do a little introduction, my name's Andrew Juniper. I'm the product owner for the Globe Claritas software. Your presenter today is Mark Henderson, who's an R&D developer for the Globe Claritas team. Hopefully everybody will find this presentation very interesting.
Well, hello everyone. Greetings from Lower Hutt, New Zealand. Nice sunny autumn day here. As Andy said, my name is Mark Henderson and I'm a research and development geophysicist at Globe Claritas. So this talk is on some recent research and development work undertaken at Globe Claritas. The work stems from requests from various clients for a technique to reduce the receiver side ghost in ultra high resolution seismic acquisition. Clients had been attempting to process such data with a standard deghosting code, finding it difficult to get consistently clean results. For that reason, we collaborated with Fraunhofer Institute for Wind Energy Systems and Ocean Geophysics to try and come up with a more robust technique. So that leads us on to the co-authors for this talk. So Globe Claritas, we have Mark Henderson, which is me, Andy Juniper, and Jonathan Ravens. From Fraunhofer IWES, Benedict Preux, Abdul Rahman Ramadan, and Julia Haberkern. And Andy has just told me previously that I think two of these people have moved on to a different company now. And from Ocean Geophysics, we've got Chris Weller and Robert Morrow. So the aim of this is that we want to reduce the effect of the receiver side ghost in high resolution shallow tow marine acquisition. And so in the usual situation of deep tow, well-constrained streamer depths and low frequency sources, for example, boomer, the processing is relatively simple. The problem is a bit more nuanced when it comes to the cases that I've discussed here. So firstly, some background on what we're talking about with receiver side deghosting. So the receiver side ghost is caused by the acoustic wave reflecting off the water surface and back down to the receiver. The water to air interface results in a negative reflection coefficient. So -1 would mean perfect reflection. It's not usually perfect reflection, but it's usually quite a strong reflection from the sea surface. So what you end up with is a strongly correlated primary, the upgoing here, sorry, and downgoing ghost, and they interfere. And the ghost arrives after the primary with a delay that depends on the receiver depth Z and the incidence angle theta. And so you end up with these notches in the power spectrum. And the notches come at factors of F0, which is the velocity of seawater divided by 2 times the tow depth times cosine theta. Actually, a lot of times in this talk, I'll talk about slowness rather than incidence angle, where slowness is sine theta over the velocity. It's just another way of talking about the incidence angle. So as you can see, we've got these notches, and what we're trying to do is boost the frequencies. Well, in the power spectral domain, we're trying to boost the frequencies in these attenuated areas. And of course, when things go to 0 in these notches, it's impossible to, well, unless you do some sort of notch reconstruction, which is a topic for another day. It's impossible to get that signal back. Of course, in the real case, we're not dealing with amplitude spectra, we're dealing with phases, etc. Just an example of some of the acquisition that we've been looking at. So it's a shallow marine environment with about 40 meters water depth for this particular survey. A single streamer consisting of 96 channels, a sparker source, and it's shallow towed, so about 1 meter approximately tow depth. But the important thing is that the exact streamer depth is unknown. The spacing between the hydrophones is about 1 meter. And in the actual case, you can see in this, I don't know how clearly you can see it, but in this one, we've actually got some missing channels, which is quite common for these sorts of acquisition. So the maximum offset's about 115 meters. We're recording at 250 microseconds, and the record lengths are about 400 milliseconds. So what are we up against with this sort of acquisition? So this is, I've generated this plot of the approximate sea surface and the streamer position. I'll discuss that further later, how we did that. The waves are plotted with about a 3 times vertical exaggeration, and the maximum wave heights are about 1 meter. So as I said before, we're towing at about 1 meter, and we've got waves of about 1 meter. And remember, that's the wave height, so the peak to trough difference is about 2 meters. And wavelengths in this case are about 10 to 40 meters in the for the water surface. So let's have a look at the same data, but this time in the frequency domain. So this is our estimate for the depth of the streamer below the water surface. So in this case, the water surface has been flattened out. And below is the frequency spectra for each channel. So from 0 to 200 hertz and up to, I think it's meant to be 96 channels, but it says 100. So the spectral calculations actually come from a 200 sample window around the pick time. So this is the clearest part of each trace. So we get nice, clean images of these notches. And the red line, if you can see it jiggling around on the frequency spectra, is the estimate for where the notch position is. So you can see that there's a very, the notch position is very dynamic, and that's sort of understandable because we're towing at about 1 meter depth or thereabouts, but plus we've got a lot of variation in the stream position and the surface of the water. So a small change in the streamer depth will have quite a profound effect on the position of the notch when you're towing so close to the water surface. Now, this last image in this movie, I'm not sure if it's covering it up, but if you look for these channels here, the estimated notch position is actually dropped off the bottom of the spectra, and that's because we're reaching the limit of how accurate the sampling limit of the data. So we can't be exactly precise about where these points are in the what depth these hydrophones actually are, and there's a good chance that they could be a lot higher in the water column than what we've shown. And in fact, if you look at the attenuation of the amplitudes here and here, then there's a good chance that they've touched the water surface and aren't working as intended. So let's first talk about the usual deghosting methods. With a straight streamer and a flat water surface, we can just simply deconvolve the recorded signal using a slowness-dependent operator in FK domain. So for a vertically incident wave, we'd have notches that come in at this sort of period. And for a more horizontally incident wave, we'd end up with notches in this sort of spacing. But when the stream is not straight, then we have to do something a bit different. And this, one of the methods of work to removing the ghost is to work in the plane wave domain. So that demands that the water surface be approximately flat still though, but it allows the cable to be undulating. And in usual deghosting processing, you have a single value, which is your reflection coefficient, which you plug into your algorithm at the start, and that is used for multiple shots. And you also have a numerical damping or numerical water level, which is used to compensate for imperfections in the operator or the data. Usually it's considered to be just to compensate for noise. Now, the problems with the usual method when you're looking at this sort of data is that the exact depth of the hydrophones is not known, and that's kind of a critical problem. And a small error in the depth can cause a big change in the operator. So if you move that notch slightly, then you're boosting the wrong frequencies when you try and deconvolve. And as I said, the sea surface is not flat, especially at these toe depths and frequencies. So you could conceive of the case where if you could measure the sea surface in depths, then you could do some sort of processing so that you could use the multi-channel slowness-dependent deconvolution, but you'd still need to recalculate your deconvolution operator for every single shot, and that's actually computationally expensive. I know it's not the popular thing to talk about computational expense nowadays, but when not all of our clients have hundreds of cores to throw at these problems and expect things to be done in a reasonable time frame. And also with the usual method, you can also get out of plane reflections. So the 2D operator might not be completely applicable when you've got a wave that's coming in at an angle to the sea wave coming in at an angle to the stream direction. And as I said before, there's often gaps in the hydrophone array, which means that if you wanted to use the normal method, then you'd somehow have to interpolate those traces. And continued on with more problems, just to rub it in. The multi-channel or slowness-dependent deghosting operator uses that only a single reflection coefficient to cope with rough sea surface and the single numerical damping parameter to cope with all the noise and the model imperfections and the sea surface conditions. But the thing is that conditions can change dramatically over very short distance when towing a streamer so near a rough sea surface. And for example, you could have the case of a hydrophone impinging on the sea surface and maybe complex reflections. And something I'll discuss a bit later is a simplified approach, which is take approximate values for the streamer depth and the sea surface and then try and flatten the sea out. And this, but to do that, you still need to get information about the streamer depth and sea surface, which is something that the method we're talking about produces. So you still need to do something along those lines. And even if you do it, then you end up with something that is demonstrably inferior to the deghosting method we propose or we have developed. So our method. So instead of doing multi-channel slowness-based deghosting, we instead perform ghosting channel by channel. call this method in some places position dependent, because we're talking about calculating the ghost parameters, the reflection coefficients, etc., for various positions in the traces. And the idea of this is not new. The basic idea, Provenzano et al. In 2020 developed some channel-by-channel deghosting code, but our method's quite a lot different to theirs. And the advantage to this method is that it avoids the difficulty of modeling complex sea surface reflections, and we measure the ghost delay and the ghost amplitude, which is effectively the reflection coefficient, directly from the data, rather than assuming it, assuming the values. And the observation data we use is from overlapping short-time Fourier transforms. And so we can estimate these ghost parameters, the reflection coefficient, etc., using, well, it's possible because we can use the notch diversity. So the notch jumps around enough that we've got enough diversity to estimate the parameters, and we've also got the fact that we've the power spectra of the ghost-free signals are smoothly varying, which helps us. I'll explain this more later. And one of the outcomes is of the estimation processes, we also get local signal spectra. So by local, I mean at various points in the traces, we get an estimate for the signal spectra of the deghosted signal. And with that information, we can actually improve the accuracy of the deconvolution operators. If you remember your Wiener deconvolution operators, one of the things you put in is the power spectrum of the signal that you're trying to deconvolve, of that you're trying to recover effectively. And this method is much quicker computationally than the slowness dependent method. Continued on. So the parameters that we're trying to estimate are the local power spectra. So that's at each point in each trace, we try and work out what the power spectra are, the ghost delay times, and R, which is, I've got in quotes reflection coefficients, which I'll explain what I mean in a moment. And that's throughout the space-time volume. So it's actually difficult to measure the reflection coefficient specifically. So R is instead the effective reflection coefficient. So noise may mean that R is estimated to be smaller than the true reflection coefficient. Overlapping rivals with different delay times can also reduce R. So in effect, R is a measure of how far we can push the deconvolution before we start to boost unwanted signals. So the method limitations, there's only one major limitation, and that is that it can't separately estimate the ghost parameters for overlapping arrivals. So you may have an arrival with one slowness and another one with another. And in the normal slowness-based method, it's possible to separate those and deconvolve them. But in this method, it estimates an approximation and deconvolves it in that way. So the procedure, the whole procedure of this method consists of multiple steps. The first one is to estimate the location of the primary and the ghost within short windows around the peak times for each trace. So in the uppermost part of the traces, you're getting a nice clear image of the notch location. Well, in this case, we're getting a nice clear image of the arrivals. which means the estimation process produces the delay time and an estimate for the spectra of the wavelet. And again, I'll explain a bit more of this later. And then that information is fed into a more extensive estimation procedure, which I was discussing just before, which is a global estimate of the delay, reflection coefficients, and spectra throughout the whole trace over the whole length of the trace in the time domain. And the estimated quantities are then used to perform causal Wiener deconvolution on each of the little short-time wavelets, short-time Fourier transforms, and then it's reconstructed into the full shot gathers. So the point is that the steps feed information into each other, which improves accuracy and computational stability. So the first part of this is estimating the delay. So we take a window of samples around the picks for each channel in a shot gather. And we make the assumption that all we're seeing in each window is a primary and a ghost. And from that, we estimate the wavelet, primary time, and ghost delay. So this is our wavelet. It's arriving at some primary time, and there's a delay, and the negative form of that wavelet comes in, and combined together, they produce an observed trace or section of a trace. And the wavelet is modeled as smoothly varying across the channels. So that simplifies the procedure. And so the estimation method is we start with a seed waveform, which could be an average over all the traces or an estimate from a previous shot gather. And we alternate between estimating delay and primary times and updating those smoothed waveforms until it converges. And the good thing about this is the range of possible primary and delay times is actually pretty small. So we can just exhaustively search the parameter space for the best fit. So that saves us having to, we don't have to worry about some sort of sparse estimation procedure. So let's have a look at the results from that first step. The algorithm is actually usually very stable, and failures are usually due to bad picks, excessive noise, or the streamer impinging on the water surface. And those things usually go together, excessive noise and bad picks, and usually are the result of the streamer getting close to the water surface. And usually the results look like these two examples from two different surveys. So we get these picks of the primary in red. So these are flattened gathers, time and channel. We get these quite good picks of the primary and the ghost in blue or green or whatever it is. And the same over here. Now, one interesting thing we can do is take those delay times that we got from the previous one, so the difference between the primary and the ghost arrival, and we can plot them out in shot channel coordinates as color keyed images, and we get these plots. So that's channel and shot, and the yellow is a greater delay time, and the blue is a smaller delay time. So there's actually some missing channels that are left in here. That's what the blue lines are. And you can see the general shape of the streamer. So we've got a deep portion here. We've got large delay times, shallow, deep, etc. But you can also see these diagonal striations. So in this one, we're getting striations that run in this direction, maybe something that runs across there. And in this one, we've got quite high frequency or short wavelength features that run across, and longer wavelength ones that run that way. So these are undulations in the streamer or ocean waves or something else along those lines. But whatever process it is, we're getting if it's a wave, a C wave, then it's coming in from different directions. So the full estimation, at the moment we've got the delay times and the wavelet estimate for the uppermost part of the traces in each shot gather, but we need the parameters for the entire trace, not just the very top part. And so we introduced this delay factor, which is multiplied by our channel delay, the delay we got from the previous calculations. So this is a single shot channels, and that's time. And the green section is the delay above the at the topmost part of the trace, and the delay factor modulates that delay time throughout the shot. And one important thing is that we can use multiple shots, in this case 5 shots. Each of these has a different channel delay, but they all share a common delay factor, which sorry, my kids are home at the moment, so they're just making some noise in the background. So if we assume that there's a similar structure, we're imaging something similar between all these shots, then we can just reuse this delay factor for each one, but the variations will be common to these shots, and that reduces the number of parameters that we have to estimate. And of course, using multiple shots in the estimation means we have much more redundancy in the calculations. And as I said before, the observation data is overlapping short time Fourier transforms. These overlap down each channel, and then so we end up with this. Once we collect all these values for each shot in each channel, we end up with an array consisting of these spectra. Now, the parameterization, to accurately model the observation data, we need to estimate the channel delay, the delay factor, reflection coefficients, and the spectra. And delay factor and R are estimated at grid nodes in time and offset space. And the constant between shots and smoothly vary within the shots. So the grid points are more densely spaced towards the upper part of the trace. So that's where the first arrival is coming in, somewhere in here. And we're following that. And we have higher resolution in this part because that's where we expect the biggest variations to occur. And the spectral are also parameterized in a similar way with the same sort of gridding, but usually a lot coarser. The other thing with the spectra is that we need to decompose the spectra between the variations that occur within the shots and the variations between the shots, because you may get a different shot spectrum depending on the conditions of your source. I mean, the source is also moving around in the ocean too, so you may end up with a different spectra for each shot. And as I said before, the reflection coefficient is intended to model not just the reflectivity, but also compensate for any deficiencies. So hopefully this doesn't get too complicated, but our observation data can be thought of as a 4-dimensional structure, which is the amplitude spectra in each of these points within this cuboid. So it's a vector of amplitude spectra in here, and sample, shot, and channel domain. And we want to decompose that information into the channel delay, which is in shot and channel coordinates, the frequency spectra for each shot, so it's just in the shot domain, and then the delay factor, reflection coefficient, and power spectra within the shot, which is in sample channel domain. So if any of you have ever looked at tensor factorization, you might be able to see where I'm going with this, because we end up using a trick from tensor factorization, which is the method of alternating least squares in order to estimate the parameters. The difference here is that the parameters we're estimating have a non-linear effect on the observations. And so combining iterative ALS with the non-linear estimations might come off sounding like a recipe for disaster. But the calculation is actually usually very stable and converge quickly. And that's because we already have good estimations for the channel delays. We also have good estimates for the frequency spectra. And so it's just a matter of doing a few adjustments to get the best solution. And the deconvolution, once we've got those parameters, the parameters for each part of each trace, we end up with these a signal we've got to deconvolve. So we have the primary, which I've set to amplitude 1 here. After a certain delay, there's a negative reflection, which has amplitude R. We want to deconvolve that from the signal, so we produce a causal Wiener deconvolution operator. And as I said before, the deconvolution operator is enhanced by the fact that we've actually got a good handle on the frequency spectra of the signal we're after. And then finally, we reconstitute the output, which just means deconvolving each of those tapered sections of the input data and then combining them back into shots, into shot gathers. So first off, let's have a look at some synthetic tests. So a lot of my previous work was in passive seismic, and those guys love their synthetic recovery tests. And the idea is that you feed in a signal into some synthetic data and see what you get back, see if you get a result similar back again. So in this case, I'm using synthetic data with semi-randomly located wavelets and their associated ghosts, and we're varying the ghost delay and offset in time space to see how well we recover. So as is the norm, a sinusoidally varying in both directions reflection coefficient, delay time I should say, just to see how, if we feed that data right from the start, do we get the same thing back? In actual fact, it comes back very similar. So the method can extract the synthetic delay. And some other tests we've done show that it's actually quite resilient to noise, and it can resolve variable R or work under the presence of variable R. So now another synthetic test, with synthetic example at least. So this is the frequency spectra for each channel. So the spectra run down, channels run across, and you can see the notch position varying. And you can see it present in here. We've got a big delay, little delay, big delay. So we put that data into the processing, and we see that see that the notch has been filled in to an extent, as much as possible, and the results look very good in the deghosted version. You may notice a slight ringing artifact, and that's just due to the fact that we can't get back any part of the signal which has gone too low. The amplitude of in the power spectrum that's gone too low. So now we look at some tests with real seismic data. There's just a little window of some data, time, channel. That's a frequency spectrum for each channel. See the notch. That's after. So the ghost amplitudes have been reduced and the primary is more clearly defined, and we've mostly filled in the notches. So the delay factor that we can extract all these parameters from each shot, and we can plot them up to see if they make sense. So in that case, the previous case that I just showed you, we can take out the delay factor and see what it's actually doing. And you can see that the delay factor actually increases with depth, especially at these larger offsets. So that's time and that's channel. And that's what we would expect, because for greater depths of reflection, you'd expect the wave to come up more vertically, and hence you'd have more delay, and that's what the delay factor is showing. And the reflection coefficient, you can see it's very close to 1 at the top, where we've got a nice clear signal, and it decreases as we go down due to noise, etc. And there's a bit of a decrease in the reflection coefficient, and that's where the multiples are coming in that hadn't been removed in this data set. So at this point, it's worthwhile talking about what would happen if you did try to use a slowness-dependent deghosting method on this sort of data. And I mean, we have the water surface and we have the depth of the streamers, so you'd think that it would be possible to somehow massage the data enough that we could put it into the normal usual methods of deghosting. So this is just an example where an example set of data where I've taken very clean seismic data and the most accurate delay time calculations and primary time calculations that I could find, and tried to process it through. So as I said, we've got to do some processing first. And the first thing is we've got to get the primary and delay times from step 1. So we can calculate the approximate streamer depth and ocean surface. And the next thing we're going to do is shift the streamers on the ocean surface till the water surface is flat. And this plot trivializes the complexity in doing this, because we actually have to work out an approximation for the travel times and ray paths of what we're seeing, and try and work out where the streamers are and how they can be shifted, how the traces themselves can be shifted on the basis of that. So it's not an easy job, and it took a lot of back and forth to come up with something that would work. And as I said, the seismic traces are shifted depending on how much we shifted the streamer on those simplifying assumptions about propagation of the waves. And the third thing we have to think about is interpolating all those traces onto evenly spaced offsets, compensating for missing traces and variations in channel spacing. And fourthly, deghost using an operator specifically generated for that streamer depth profile. So it's not an easy task. And this is probably one of the simpler methods I could think of to try and do this. So this is in the near offsets, so the first 20 or so channels. This is before the deghosting. That's the slowness dependent, which is just the normal method. This is the position dependent that we're discussing here, or we're discussing. So the first thing is that there's actually similar degrees of deghosting in the upper parts, we've recovered similar amount of the frequencies in those parts. But the slowness dependent has quite a few artifacts before the first arrival. Some of that's just ringing, and it's occurring before the trace, the start of the trace, because it's not causal, the deconvolution. And you also notice that there's a little bit of ringing after these, though, in these traces here, the very slight ringing artifact, and that's because the delay is quite large in those positions, and where the notch has moved into the largest amplitude in the input signal, so it makes more of a profound effect. And the slowness dependent is more aggressive in deghosting further down, and that's because we've only got one parameter, well, two parameters, effectively the reflection coefficient and the damping parameter, to process the whole thing. So it will be more aggressive in places when it probably shouldn't be. In this case, it probably shouldn't be so aggressive, because we're actually generating quite a bit of noise in this region. And in the far offset, again, we're getting quite a lot of noise before the onset of the first arrivals in the slowness dependent. And again, similar deghosting the upper part of the traces, but the slowness dependent has actually lost some detail in these lower parts, and that's because it's estimating the output. It's not just deconvolving it. So if there's a problem, then it can just ignore bits of the data. So the point is that if you really want to do slowness dependent processing, then you can with a lot of effort, but the result, I don't think, is as good as just using position dependent method. So some more processing results for the position dependent method. So these are 4 different shot gathers, and this, I think it's this box here, seems to be 2 boxes for some reason. We've got the power spectra, so CDP channel and frequency up to 2000 hertz. So that's before any deghosting, and that's after. Before, after. Now let's have a look at some stacks after pre-stack time migration. So we're just looking at this little box here in the data. Again, we seem to have 2 boxes in here. So that's without deghosting, and that's with. Without, with. So with deghosting, we end up with crisper images of our interfaces, and we also have a bit more coherence. And we can also look at the frequency spectra. So this is CDP number and frequency on the vertical. So it's without deghosting and with deghosting. So you can see that we're getting a much broader amplitude spectra here. It's much better filled in. We're getting more towards lower frequencies and the higher frequencies. And then looking at the average of all the traces, all the post-stack data, we can see that the frequency spectra are significantly improved, especially in the low and medium to high frequency range, getting about a 4 dB improvement in these lower frequencies, around 125 hertz or so. So final thoughts. For the case of shallow toe high resolution seismic data, our method generally produces better results in slowness dependent deghosting, and that's not taking into account all the things that go along with that, slowness dependent deghosting, all the pre-processing, etc., which is also quite an annoyance. The ghost in this method is attenuated where it can be done so safely without adding significant artifacts. So we saw before that if you just have a common reflection coefficient throughout, then you can end up boosting things that you don't really want to boost. So in this case, we're estimating for the data reflection coefficient, so it's sort of tailor-made for the specific circumstance. And although by no means fast, this method is still many times faster than all the numerical integrations you have to go through to estimate your slowness dependent operators for each shot. And as I said, the data require no pre-processing before being used, such as interpolations and time shifts. And also the fact that working with 1D signals mean that we can do a much better job on our deconvolutions. So we can use causal Wiener deconvolutions with the signal spectra. And so that results in cleaner deconvolutions. So overall, faster and better.
If people do have questions that they would like answered, then obviously feel free to contact the Claritas team, and we'll happily respond via email if that's to any of your questions, if you think of anything after the fact. But otherwise, thank you for attending this webinar, and hopefully you found it interesting and useful.
Yeah, thanks everybody.